Okay guys, let's have a quick look at this one here. So if I want to find average velocity, okay, average velocity is total displacement over total time. Okay, for this graph, for each section, okay, that might mean that I have to do this. Final position minus initial position over time. Pretty common thing to have to do on a position time graph because, well, you have position and time. You want to use a formula that has position and time in it. That would be this. All right, so for part A, okay, and you probably didn't even bother doing this one because you could just do it in your head, right? The final position was positive 25 kilometers, okay? The initial position was 0 kilometers, and the time for that was 1 hour, so you got positive 25 kilometers per hour, right, for your velocity for the first one, okay? And then for the second one, okay, so from 25 to 33, right, you would have, again, done the same thing, except you would have gone positive 33 minus positive 25, and that took 1 1/4 hours, because it ends up right in between these two times, so 1.25. Okay, and if we do that, we should get positive 6.4 kilometers per hour for that one. Okay, does it make sense that that one is slower, like just looking at the graph? Right. It's not as steep, right? It's quite shallow. All right, and then for part C, sorry, that's the velocity in B. Okay, this is the velocity in A. All right, and then for the velocity in C, okay, we would have our final position, 27, minus our initial position, 33, which is why we get the negative number, and that also took 1 1/4 hours. Okay, so when we do that one, we should get negative 4.8 kilometers per hour. And again, that also makes sense. That probably has the smallest slope, okay, just kind of looking at it of all the parts of the graph. Okay, questions on how that works? Okay, that's a pretty typical kind of position versus time graph question. Okay. Now, well, sorry, last part. We got to do the average velocity over the whole trip. Is it the same calculation we've done now 3 times? Yeah. Okay. Average velocity over the entire trip is going to be 27 minus 0 over 3.5 hours. Okay. And that's going to give us positive 7.7 kilometers per hour. Okay. So all this car did was go forward and then backward a little ways. Okay. All right. Any questions on what we did there? Okay. If you were in my Science 10 class, you've seen that graph before because I put it on a quiz. Okay. So you've definitely seen that one before. Okay. For our lab tomorrow, okay, if everyone can just write this down, when you have your phones, you need to go into the App Store and you need to get this app. It's called Spark View. Okay, it's free. Okay, don't get the paid version. There is a paid version. Don't get the paid version. Okay, we just need the free version. That app will allow you to use your phones tomorrow, which I will allow. Okay, to collect data for our position versus time lab. Okay, so it will communicate Bluetooth to our little powered carts. Okay, and they transmit Bluetooth back to your phone, and they will record the position of the cart 20 times per second. Okay, as they travel along our level surface tomorrow for our lab. Okay, it makes data collection super simple. Okay, the first time there's a bit of stuff you have to learn, but once you've learned how to use it, okay, it does a great job of collecting data, and it doesn't involve having to put sticky notes on the floor of the atrium while you follow a motorized cart along the floor. Okay, if you were in my Science 10 class, we did one like that. I think Mr. Everett did too. Okay, all right. So that's the app that you'll need, Spark View. Okay, the icon is like a blue background with like a circle made of white dots on it. Okay, something like that. All right. Let's talk a little bit here about, well, actually, before we go to that, what if I gave you this graph and I asked you, what's the acceleration of the object in part B? That would be a 1-mark question, and it's mostly just an interpretation question. There's actually no calculation involved here.
0.
It's 0. How'd you know that?
Because it's a straight line.
Yeah. On this graph, if I have a straight line, it's telling me that the position of the object is changing at a constant rate. In other words, the object is traveling at a constant velocity. In order to be accelerating, its velocity has to change. That looks different. What is the shape of acceleration on this graph? Right? Curves of any kind. You see a curve, then there's acceleration going on because that means the velocity is changing. If the lines are all straight, okay, then we're talking about constant velocities. Different constant velocities, but constant velocities. I play that trick all the time, guys. I'm just going to put it out there. Okay? I ask people what the acceleration is on position versus time graphs all the time, and you wouldn't believe the amount of work that people show for a 1-mark question for which the answer is 0. Okay? And they'll do all this proof that's wrong, okay, and give me a number that's also wrong, right? Because they don't recognize, hey, I can look at this graph and tell right away there's no acceleration here. Okay? Now, it is very, very difficult, like nearly impossible to calculate acceleration off of a position versus time graph. Okay? So if you're ever asked for it, it's not something you could do. Okay? We're going to look at like 5 or 6 different acceleration formulas this year. Okay? And you really can't get the information you need from a position versus time graph to use any of them. Okay? Last year, when we learned about acceleration, this was the formula we used. The only part of that formula that's on a position versus time graph is time. Okay? It's pretty much impossible to get acceleration with what you can read off of a position time graph. Agreed? Okay? Just something to watch out for, right? That's one of those questions that's super simple if you're interpreting graphs correctly, okay? And guys, we are really big on the interpretation of graphs. We know you guys can do V equals D over T calculations, okay? I mean, that's like almost beneath you at this point. But being able to look at a graph and tell me what's happening, that's important because that's a skill that can be transferred to any kind of graph. And as I was saying the other day, in Physics 30, you could have, 45 to 50 different graphs that you're going to have to interpret. Okay? Having those interpretation skills is way more valuable. Okay? All right, let's quickly talk about velocity versus time graphs. This is also review from Science 10. We're not teaching you anything new, okay, with velocity versus time graphs that you didn't learn in Science 10. Okay? All right, so velocity versus time graph, okay, tells us how fast and in what direction the object is going at various points in time. It tells us its velocity and at what time it had that velocity. Those are the things you can read directly off the graph. Okay? There's lots of other things that we can interpret and calculate. In fact, there's way more that we can calculate on a velocity time graph than on a position time graph. Okay? Now, on the screen here are a position versus time graph on the left and a velocity versus time graph on the right. What do they have in common?
They're both graphs.
Okay, absolutely. They are both graphs. What else do they have in common? Sorry, the time. They run for the same amount of time. What are both of them showing?
That they're traveling at a constant velocity.
Yeah. In fact, these graphs are of the same object because they both show an object traveling at a constant velocity of about 260 meters per second. Okay, like on the velocity versus time graph, we see a flat line. On that graph, that doesn't mean it's standing still, it means the velocity isn't changing. That's what this graph says too. Okay, it says the velocity isn't changing, that it's covering the same, it's changing its position by the same amount every second. Okay, do they look much alike? They look quite a bit different, don't they? Okay, but they are telling me the same thing, and there's a way to verify that. Okay, can I calculate the velocity of this object from this graph? Right, I could do this. Right, I could go V equals D over T, or I could also do this, M equals Y minus B over X. It's the same thing. It's final position minus initial position over time. Okay, so I'm just going to do that. I'm going to take my final position here, 1,400 meters. I'm going to subtract my initial position, which is 100 meters. And that takes 5 seconds. All right, 1,300 divided by 5, I'm pretty sure comes out to 260. Yep. They're definitely showing the same object. Okay? Both of these are showing an object traveling at a constant velocity of 260 meters per second. Okay. So what's the acceleration of this object? 0. Both the graphs say that, right? There's no curve on this graph, okay? And this graph is clearly showing that there's no change in velocity. And that's what acceleration is, change in velocity. So no acceleration going on. On this graph, this top part here, I went final position minus initial position. So this is the displacement of the object. Would you agree? Okay. Could I calculate that displacement from the other graph? Okay. I mean, I know the speed or the velocity it's traveling at, and I know how long it's traveling at that velocity. Can I calculate its displacement? Gee, lo and behold, it comes out to the same number as the other graph. Okay. Now, here's a little trick you probably picked up in Science 10. Okay. I just calculated the displacement of the object from my velocity versus time graph, and I took the time, 5 seconds, and I multiplied it by the velocity, 260. I went base times height. I found the area under the line, or between the line and the x-axis. Okay, does that little rule kind of ring a bell for anybody? Okay. Now, it's okay to kind of have that in your back pocket or in the back of your mind. Okay, that's how I calculate displacement from this kind of graph. But we want you to understand why that works. Okay, that works because the base of any velocity versus time graph is going to be time, and the height is going to be velocity or average velocity, because that's all we did here. Okay, all we did when we went base times height is took average velocity and multiplied it by time. That's why it comes out to displacement. Okay, everybody with me so far? Okay. Now, let's take all of that away and do this. Okay, what's that object doing?
Accelerating.
That object is accelerating, okay? The value of its velocity is clearly increasing over the 5 seconds, okay? Could I calculate its acceleration? Could I use the formula we learned last year? Absolutely, right? Like we learned this formula last year. A equals VF minus VI over T. I can read those two numbers off the graph. I could totally get the acceleration of this object. Okay, so VF would be 400. VI would be 100. Time is 5 seconds. Okay, so it should be what, 16 meters per second squared? I think. Right, 300 over 5, pretty sure that's 60. Okay, so this object goes 60 meters per second faster every second. Is that pretty fast? It's really fast. It's 6 times faster than you fall. Okay, when you fall, you accelerate at 9.81 meters per second squared. This thing is accelerating at 60 meters per second squared. That's really fast. Okay, that's like 6 G's. So you would, if you were in riding this object, you would feel 6 times heavier than normal. Okay? Like Top Gun-ish, blacking out, kind of. Yeah, that's how you would feel. Okay, now when I calculated that, okay, What else did I calculate about that line?
The base and the height.
I used the base and the height. I used them to calculate something about that line. Look at the arrangement of this formula and tell me if it looks like this one. It looks like that one because it is that one. Okay, that formula that we learned last year in Science 10 to calculate acceleration is just the slope formula. Okay, it's just applied to this graph. Okay, so on a position versus time graph, when we calculate the slope, we're dividing position by time. We're going meters divided by seconds. We get meters per second. On this graph, when we find the slope of the line, we're taking velocity and dividing it by time. Or dividing meters per second by seconds, which gives us meters per second, or meters per second squared. Okay, so slope on this graph represents acceleration. Every graph slope represents something different. Okay? But it's not hard to figure out what. I just have to look at what am I dividing when I plug it into that formula. Okay? It becomes pretty evident pretty quick, right? So here's final velocity minus initial velocity divided by time. Okay? We're just calculating the slope with that formula. Okay, this line here. Let's actually let's do this just so I've got a 0 on the bottom. Okay, that's an accelerating object, agreed? Okay. Calculate its displacement for me over the 5-second interval. Okay, we're going to assume it goes up to 8, okay, and over to 5, obviously. Okay, I'll give you a minute on that one. Okay, on this graph, I've got an accelerating object. Okay. It is accelerating from 0 meters per second to positive 8 meters per second over a 5-second interval. Correct? Okay. Now, I was asked, calculate the object's displacement. Okay, and to which I said, go ahead and use that thing you learned last year about area. Okay, so everybody went, okay, the base of this triangle is 5, okay, and the height of this triangle is 8, and the area of a triangle is the base times the height divided by 2. Okay, so when you did that, you went 5 seconds times 8 over 2, okay, and you probably got 5 times 4, 20 meters. Okay, absolutely right. Why does that work? When it was a rectangle, it was easy to justify how it worked. I went velocity times time, but the velocity was constant. Okay, so it was average velocity times time, but the object wasn't changing its velocity. Here it is. Why does calculating the area still work, even though this object's doing something different? Okay. When we did the rectangle, we still did this. Average velocity times time equals d. You still did that here. Because if this object accelerates from 0 to 8, would its average velocity be right there? Halfway up, right? Half the time, you're going to be going slower than 4 meters per second. The other half of the time, you're going to be going faster than 4 meters per second. And it's all uniform. That means your average velocity is half of your maximum, or halfway between your initial and your final. Okay? So it makes sense that when you take the height and divide it by 2, that you would be finding the average velocity for an accelerating object. Okay? Everybody okay with that idea? All right, so that's why that area under the line part works. Okay? You're still doing time multiplied by average velocity. Okay, you're still doing it. Questions there? Ringing a bell? If you were in my class, you better be doing this because I totally taught you exactly that. Okay, last year. Okay. Okay, so here's a graph of a person who's running. It's a velocity versus time graph. Okay, what's the object doing in this first part right here?
Getting faster.
Yeah, they're accelerating, right? They're going faster and faster. Okay, it's a little bit curved at the bottom. We sometimes see curves on velocity versus time graphs because, well, at the beginning you're kind of coming out of the blocks. Your acceleration is not very uniform. Your first few steps are, I'm regaining my balance but trying to push forward. Okay, and then as we get towards the top here, we see that the rate at which they accelerate kind of levels off. Okay, what happened right here? They reached their top speed. Okay, as you're running, I mean, you've all had this experience. You run as hard as you can, you accelerate, and then you can't anymore. It doesn't matter how hard you try, you simply cannot run any faster because you cannot push any harder. You reach your top speed and all you can do is maintain it until you, well, tire out. Okay, so that's what happened here. Their acceleration changed because it got to a point where they couldn't force themselves to run any faster. And then they ran as fast as they could at their top speed, right? And then I would assume they probably crossed the finish line, and that's what the last part would be. Okay, crossing the finish line. Did they stop?
They slowed down and they did stop.
Looks to me like they stopped. Does their velocity reach zero? That means they stopped. Okay, that's a trick question. I mean, it's not really a trick question. It's kind of a trick question. I could put something like that on a unit exam as a multiple choice question and say, did this object stop? Okay, and a lot of people would say no, because it doesn't feel like looking at that graph they did. They're telling me velocity. Well, did the velocity become zero? If it did, then they stopped. Okay, there was a time where they were accelerating. There was a time where they were running at a constant velocity. There was another time where their acceleration was negative. And then, after that negative acceleration, they stop. Okay? Their velocity reached zero, and that's where the data ends. Okay? Now, if you're an athlete or you're looking to be in like the training kind of field, physiotherapy, kind of things like that, graphs like this can actually be an important analytical tool. High-level athletes, okay, will have their trainers and coaches and stuff analyzing this kind of data, okay, in order to help them improve. They'll want to see, okay, maybe this is a person who is just got a great top speed, but they're not very powerful. Okay? So once they reach their top speed, nobody can catch them. Their problem is it takes them a long time to get there because they're not super powerful. Okay? Other people are extraordinarily powerful, but usually if they're very powerful, they're also kind of more muscular, a little more bulky, and they probably don't have that high of a top speed because maybe they have shorter legs. Or, well, if you're really big and bulky, you're forcing a brick through the air because you're a brick, okay, and you're big and square, okay? I mean, and that happens. There's different kinds of athletes, okay? And so what you want to do is you want to focus on, okay, where can we improve? Okay, a prime example, okay, could be like Usain Bolt, okay? Usain Bolt was not a typical sprinter. He was like 6'8", and he was actually kind of lanky. Okay, he wasn't really thick and powerful like most sprinters in the modern era are. Okay, there have only been a few sprinters that are kind of the same body type as Usain Bolt. One of them is Donovan Bailey, Canadian sprinter who was for a while the fastest man alive. Okay, another one would be Carl Lewis from back in the 80s. Okay, they were kind of tall and lanky, but most sprinters are smaller and bulkier, and they're all about power. Okay, so when you watch them run against each other, okay, like anytime you watch Usain Bolt run, he's like the last guy out of the starting blocks, and he's always at the back of the pack. But he reels everybody in because his top speed is just so fast. All these other guys get out quick, and they're at their top speed in the first 25, maybe 30 meters. Usain Bolt takes 60 meters to reach his top speed, but it's blinding. Okay, dude runs at like 18 meters per second. Okay, to give you some idea, that would be from that wall pretty much all the way through the chem lab. okay, in terms of 1 second's coverage when he's running at his top speed. It's actually why he's a better 200-meter runner than a 100-meter runner. Once he gets to that speed, good luck, he's gone. All you're gonna see is him getting further and further away. Okay? But in a short race, like Usain Bolt would never win a 40-meter race or a 40-yard. Okay, like something that's a strength test you do in football, right? Like you do the 40, right? I want to know how fast I do the 40. That's a power measurement. Okay, how fast you run the 40 is all about how quickly you can accelerate, and then you can rate your power, okay, based on that, right? Football, unless you're a wide receiver, maybe a running back, is not about top speed. It's about how quick can I get there, okay? How quick can I get to my top speed? Because you're rarely going to run more than 30 or 40 yards before somebody tackles you, okay? So different sports are going to analyze this kind of data differently. Okay, and it can be an important measure and guidance, okay, for the type of training that needs to be done. Maybe you got to get in the gym and lift some more weights, okay? Or maybe you need to, develop a different muscle type and be a little leaner as opposed to powerful. All right, so on a velocity versus time graph, you don't need to write this. This is stuff you already know. Okay, the vertical value of any point is the instantaneous velocity. Basically, I'm saying on a velocity time graph, you can read velocity in time. Surprise, surprise. Okay, and we also learned area under the line on a velocity time graph is equal to the displacement of the object. Okay, and that is because what you are really doing is this calculation. Average velocity times time. That's either base times height, or it's base times height over 2. Okay? This and this both calculate average velocity. And then obviously the base is time. Okay? So important thing to know, that's absolutely something that could be on next week's quiz. Okay? Acceleration and velocity time will be next week. This week will be position versus time and V equals D over T. And how many people have had a look at a couple of the quizzes already? Okay. If I ask that question tomorrow, I should see a lot more hands. Okay? Because, yeah, I guarantee you it's worth your while. All right, so let's look at okay, I want you guys to write this one down, okay? I don't want you to actually graph it. I just want you to solve this as a V equals D over T problem, okay? So write this one down, try and solve it, okay? And then we're gonna talk about not only this one, but a way in which I could modify it, okay, to test something else, right? So I want you to write it down because it's a good example. Okay, so just the stem here, these are your givens, which you would write down anyway, okay? And then you can show your solutions there, okay? I'll give you a couple minutes on that. This one's pretty straightforward, agree? Right, it's just a simple V equals D over T problem, but 2 of them, right? So we're doing this for 2 different people, okay? Student A is gonna end up 300 meters, okay, east of the school, okay? And the other person's gonna end up 450 meters west of the school. Both of them are gonna walk for 3 minutes. All right, so for student A, okay, obviously the speed or the velocity of student A would be positive 350 meters divided by 1 minute. Okay, we could have this in meters per minute. If you converted it to seconds, that's also fine. Okay, sorry, 300 meters, not 350. Okay, and so that's going to mean 100 meters per minute, okay, east for that person, and the other person, they're going 450. Okay, so for student B, okay, that's going to be negative 450 meters because it's west. Okay, and in the same amount of time, 3 minutes. Okay, that should be 150 meters per minute. Per minute west. Okay, if you put it in meters per second, that's fine too. Okay, everybody with me there? All right, here's how I would change a question like that. All right, I would say that both of the students do this and then realize they have to go back to the school. Okay, and they come back to the school in exactly another 3 minutes. Who had the greater velocity? Okay, so if they both do this walking, okay, this student here, okay, student A goes 300 meters out and comes 300 meters back to the school, that all takes 6 minutes. This person goes 450 meters, then comes back 450 meters in 6 minutes. Who has the greater velocity? Neither. They have the same velocity. What's their velocity? 0. Where did they both end up? Back at the school. Okay? That's, I mean, it's a trick, right? It's absolutely checking if you read a situation carefully. All right? But I've had, people answer a question like that and they're like, here, this is so easy. Why did you insult me with this question? That guy went 900 meters. This person only went 600 meters. You think I'm dumb? And then I have to answer kindly, sort of. Okay? Because what was the right answer? The right answer was they had the same velocity. They both ended up back where they started, but you didn't see through the question. Okay? There's often little details like that, and that's what I'm looking for. Do you understand the difference between speed, which is what they're telling me about? This person went 900 meters, that person only went 600 meters, that person's faster. That's absolutely right. That 900 meter person, okay, this guy here who went out and back, he was faster. I didn't ask who was faster. I asked who had the greater velocity. That's magnitude and direction. It's a scalar vector question, right? Now, if you read that question carefully, how much math do you need to do? None. That's why it would probably be a multiple choice question. Okay? There's no calculating involved in a question like that. It's strictly realization or recognition. Okay? Everyone follow on a question like that? Okay. I don't want to do the wildlife biologist one. Okay. I would like you guys to try that one. Okay? So velocity versus time graph. Okay? And we want the displacement and the average acceleration over the entire 10 seconds. Okay? Well, one of those is a little bit of work. Okay? The other is less so. Okay? You can think about your shapes rule from last year for that. Okay, so the first part wants to know the displacement, okay? And part of doing that is recognizing what's the object doing in the 3 parts of this graph, okay? Obviously in the first part, it's traveling at a constant velocity, okay, of 3 meters per second for 4 minutes, okay? And then it does what?
Slows down.
It slows down, okay? So there's an acceleration part here, okay, which means it's going to be going a bit slower, but I know that I can calculate the displacement during that part because I have the initial and final velocities, all right, so I can get the average velocity in there and multiply by the time, get the area of that triangle, okay? But I also have this little piece underneath there that represents, here's what the object would do, okay, if it was only traveling at that final velocity for the entire time. I have to take that into account, okay? So what I do is I just make it part of this part of the graph that represents the object traveling at 1 meter per second for the next 10 minutes. Okay, everybody with me there? All right, now before I do any multiplying, I probably want my time to be in what? Seconds, just so my meters per second and my time units match. Okay, so to calculate this one here, okay, that's going to be 3 meters per second times 240 seconds. Okay, so that's going to be 720 meters. Okay, and then I'll do this rectangle too because that's fairly easy. Okay, we got 1 meter per second for the next 6 minutes. Okay, so that'll be 360 seconds, I think. Okay, so that's 360. 1 times 3. I almost typed that into the calculator. I almost typed 1 times 360 in there. I was close. At which point you should have all pointed and laughed at me for doing so. Okay, positive 360 meters. Okay, and then I've still got that little triangle there. Okay, so the base of that triangle, okay, would be 1 minute or 60 seconds. Okay, and the height of that triangle, it goes from 1 to 3. So the height of that triangle is 2, okay, meters per second. Right, so that's going to be 120 meters in there. Okay, what did I do wrong?
Forgot to divide.
I didn't divide it by 2. You got to catch me. Sometimes I do that on purpose just to see if anyone's paying attention. Okay, all right, so it's actually just going to be 60. Okay, what do I do with those 3 numbers? Megan, what do I do with them? Add them up, right? Okay, this is just 3 things I got to add together. Okay, so 720 plus 360 plus 60. Okay, so 1140 meters would be our total displacement for this, and it would be positive. Okay, everybody with me there? Is that ringing a bell from last year? Okay, I would have absolutely given you a graph just like that. Okay, want to calculate the acceleration. Now, I can't find slope here because I don't have one single linear function. But I can use that formula because I can read the final velocity, the initial velocity, and the time off of that graph. Okay, so final velocity, 1 meter per second. Okay, minus the initial velocity, 3 meters per second. Right? Divide that by how long it took. Okay, 10 minutes. Okay, so that's 600 seconds. Okay, so I'm going to have on the top there, -2 divided by 600 seconds. It's a pretty small acceleration, wouldn't you agree? And it should be. That is a minuscule change in velocity over a 10-minute interval. Okay, going from 3 meters per second to 1 meter per second over a 10-minute interval, you'd almost not even notice that if you were watching the object do it. Okay? All right. Is it okay that it comes out negative? It should. The object is slowing down. I should get a negative acceleration for that. Okay. All right, I'm going to slightly spoil this one by telling you this is like absolutely my favorite velocity versus time question out of this book. Okay, that's not actually saying all that much because there aren't that many good ones. Okay, but okay, this one's a good one. So I want you to just draw a rough version of that graph. Okay, and then I want you to answer those 3 questions. Okay. The spoiling part here is there is a bit of a trick on this one, okay, for one of the 3 things. Okay, let's talk about part A here, right? Is the acceleration in part A here, is it positive or negative? Negative, right? Its velocity is becoming more negative in that part. It goes from -2 meters per second to -4 meters per second, and it does that in 1 second. So as part of part C here, I could easily calculate the acceleration in that part, okay? VF minus VI over T, so that would be -4 minus -2, okay? Which would give me -2 meters per second divided by 1 second, so -2 meters per second squared, right? It took 1 second for it to go 2 meters per second faster negatively. All right, what's the acceleration in part B? What's it doing in part B?
Going at a constant.
Moving at a constant velocity of -4 meters per second, so there's no acceleration to calculate there. Okay. In part C, is the acceleration positive or negative? Negative. It's still going faster in a negative direction. The value might be getting bigger, but it's backwards. Okay, so basically this is a person who's running backwards and trying to go faster and faster backwards. Okay, actually I think it's supposed to be a bird. Okay, all right, I don't know how a bird flies backwards, so we'll have to say it's just going west or something, and west is negative. What's going on in D?
Just coasting?
Just coasting, yep, going at a constant speed of -6 meters per second. Oh, sorry, it's north. North is on here, so that would be south, okay? E, is it accelerating? Is that acceleration positive or negative? Positive, yeah, okay. I mean, if we calculated it, we would get a positive number, but also we can see the velocity is becoming more and more positive. Now, does that mean it's going faster the entire time of part E? For part of it, it's actually going slower. Okay, now this goes to part C here. At what time does the bird change direction?
8.5 seconds.
8.5 seconds. Okay, most people's gut instinct is 7 seconds. Okay, did the bird change direction here? It's still flying in a negative direction as long as the line is below the x-axis. Okay, so this is a graphical interpretation question. It's not a calculation question. It's just looking at this and going, yep, this is a velocity versus time graph, so as long as the line is down here, it's moving backwards. If the line's up here, it's moving forwards. So right here is where it actually changes direction. Okay, so this would be a bird that was like flying south and then did this and started going north, just turned around. So like right in the middle of that turn would be 8.5 seconds. Okay, everybody follow me on that? Okay, that could easily be a multiple choice question. Okay, it's just an interpretation thing. And I would absolutely make 7 seconds one of the options. Okay, it would probably be a very popular option because you get into a test and you're a little bit anxious. It's easy to make that kind of knee-jerk reaction on something like that. We see the line change, so we automatically make an assumption. Okay, so important to interpret graphs very carefully. Sorry, I'm looking for the question I want here, guys. I'm not seeing it yet. That's not it. That's not it. Did that one already. That's the one I was looking for. Okay. I want you guys to give this one a try. I want to know the snowmobile's average velocity. This is a velocity versus time graph. So calculating average velocity actually requires you to do a bit of work before you get to the v equals d over t part. Okay, so we'll just imagine that these kind of look a little bit curved. We'll just say that they're straight. It's actually just the way I scanned it. I think the book was a little bent, so it looks curved. Okay, but these are all just straight lines. Okay, this one goes across to 40. Okay, that one goes across to 80, 20, 50. Okay, so I would like the average velocity of the snowmobile during parts A, B, and C, as well as over the whole trip. Okay, if I want to calculate average velocity, what two things do I need first? What do you think? What do I need if I want to calculate average velocity? What's in the formula? V equals d over t. I need displacement and time. I have the time, time's right on the graph, but I have to calculate the displacement, which means doing a little bit of shape calculating here, right? I would need to calculate this shape here, this triangle, and then I would probably alter this so that my rectangle went all the way to the end, and then I just had that little triangle on the top, and that would get me my total displacement, okay? But if I want to get just the displacement for this part, obviously I need just this rectangle here, okay? So let's find the displacement for part A. It goes for 20 seconds, goes from 0 to 40, okay? So base times height over 2, so 20 times 20, okay? That should be 400 meters. Okay, and then for this rectangle here, it's 30 seconds. Okay, it's 40 meters per second, so that should be 1,200 meters, positive. Okay, this little rectangle here is 10 seconds by 40, so that should be another 400 meters. Okay, and then this one here is 40 high, 1 on the base, but it's a triangle, so that would be 200 meters. Okay, well, now I've got my displacements for everything. Can I calculate my velocities for each section? Okay, so for section A, okay, velocity in section A is going to be positive 400 meters divided by 20 seconds. Okay, so that's going to give me my 20 meters per second. Okay, here the average velocity, I don't even need to do this. What's the average velocity in part B? Like I have that area because I need it for the last part of this question, but what is it doing in part B?
Coasting.
Coasting, traveling at a constant velocity of
40
40 meters per second. I don't need to do any extra work. I can just read that one right off the graph. Okay, velocity in part B is positive 40 meters per second. I can just read that off the graph. Okay, now same thing for this one here. Okay, this one here, it increases from 40 to 80. So that would mean that the average velocity would be halfway in between would be my thought, right? Between 40 and 80, halfway in between should be 60. Okay, now, if I want to get the overall average velocity, okay, so VO, that's going to be the total displacement, which I can now calculate, okay, over the total time, which I can read off of the graph. Okay, so I've got 400, 1600, 2000, 2200 meters. Okay, and that took 60 seconds. Okay, so that should give me, I don't think that comes out to 37.3. Okay, 2200, okay, divided by 60 seconds. Okay, 36 point, well, I don't know why I had 37.3 there, but okay, looks to me like it should be 37 meters per second. And that would be positive. Okay, everybody all right with that? Okay, not a ton of calculating there, okay, but a little bit. Okay, we have a couple of minutes here, so I just want to quickly talk about significant digits. Okay, how many people have done significant digits already? Okay. So for significant digits in physics, okay, well, what we have to understand is that significant digits allow us to maintain the accuracy of our measurements even when we're doing math with them. Okay, I can't take a number like, let's say I measured a distance to be 4.0 meters, and then I measured the next distance to be only 16 meters. Okay. This number here is measured to plus or minus 10 centimeters. This is measured to plus or minus 1 meter. If I need to add these two to get a total distance, I can only be as accurate as my least accurate measurement. So when I add these together, my total distance is going to be 20 meters, period. Okay, I can't put a decimal on there because I don't have that measurement for this number. Okay, so significant digits make sure that when I'm putting numbers together, okay, doing calculations with them, my math doesn't magically make my measurement suddenly better. Okay, they make sure that my final answer is never more accurate than the least accurate number I used to arrive at it. Okay, that's the purpose of significant digits. So, rules for adding and subtracting. Okay, look at your decimal places. Okay, you can never be more accurate than your least accurate number. That's my least accurate number. I can't have any decimal places here. Okay, same with subtraction. With multiplying and dividing, okay, if I multiply, let's say, this number here, okay, my final answer can only have one significant digit because my least accurate number has one significant digit. So my final answer here is 6. Okay? Right, that way my answer doesn't become more accurate than something that I used to get at it. Okay? All right. How do I know whether a number is significant or not? insignificant digits. Any value that's not a 0 is a significant digit. Because you wouldn't write it if you didn't measure it. Okay? Like I wouldn't have written 2.01 unless I was sure that number was a 1. Okay? I put it there because I measured it. All right? So any number that's not a 0 is a significant digit. 0 is the only thing that's tricky. Okay? Is this 0 a significant digit? If I measured that number, I know that number is accurately a 0. Okay? I measured 2 meters and 1 centimeter. I know that there were no tenths of a meter to be measured there. Okay? Trapped zeros, like this, are always significant. Would I bother to write those zeros if I didn't measure them? Why would I? Right? I don't want to write zeros for the fun of it. It takes extra time. Okay? I wouldn't write this number is 16.000 unless I was sure all those zeros were actually there. Okay? So these numbers, trailing zeros, are significant. Okay? These are not. Okay? Leading zeros are never significant. Trailing zeros are always significant. Trapped zeros are always significant. That's really the only trick that can come up in a significant digit kind of thing. Okay? Because any number that's measured, okay, is a significant digit. I didn't measure those. This is my biggest number. Okay? There was nothing to measure here. Another way you can think about it is, if I wrote this number in scientific notation, would I keep those? If I wrote that number in scientific notation, would I keep that one? I would. Okay? It's a measured value. Don't stress about significant digits too much. In physics, 99% of the time, if you write down your givens exactly as they appear, your final answer will have the same number of digits as whatever your least number of digits is in your givens. Okay? So if I gave you a question like this, okay, and I said your initial velocity was positive 1.2345 meters per second, your final velocity was 2.7 meters per second, okay, and the time was 1.63 seconds. Find the acceleration. How many significant digits can my answer have? 2, right? This number here has 1, 2, 3, 4, 5 significant digits. This one has 2 significant digits. This one has 3. Least accurate is 2. Answer, 2. Okay, I can have 2 significant digits in my answer. That rule will work, I kid you not, 99% of the time. Okay, there's like the odd case where there's some little weird rule, okay, that came up. Okay, 99% of the time, write that down, write down your givens. As long as you use that number, that's the key. Okay, if I did a calculation but I didn't use this number, it's as accurate as the least accurate number I used. Sometimes that'll come up. Sometimes you get a question that gives you information you don't use. That's a pretty common trick. Okay, we'll talk about that as we go through here for the next week. On Friday's quiz, I won't be worried about significant digits, but by next Friday, I will. Okay, because we're going to kind of talk through it and use them a lot this week. All right, we will leave it there, guys. Good job today.